What I have before me now is a block diagram for the homework assignment, which will examine the bit error rate performance of an optical communication system using on-off keying, or what's also known as intensity modulation with direct detection. We'll be examining the effect of noise and the effect of filtering and pulse shape on system performance. In the homework assignment, you're asked to generate several curves for bit error rate versus the transmitted power, or equivalently the received power. In this system, there are three types of noise that we're going to be examining. There is the ASC noise, or the amplified spontaneous emission from the use of an optical amplifier. There is also the noise added in the electrical to optical conversion by the PINN, the photodetection process. When using a PIN diode, you will introduce both thermal noise and shot noise. So the three noise types are ASE, shot noise, and thermal noise. Another thing that you're asked to do is to examine the impact of transmission rate and filtering on the communications link. We'll consider both 10 gigabits and 40 gigabits per second transmissions. We will look at three different kinds of pulse shapes. So here we have P of T representing the pulse shapes. We'll consider first a rectangular non-return to zero pulse shape. We'll also examine rectangular return to zero with 50% duty cycle, where halfway through the bit interval the rectangle transitions to zero. Since RZ rectangular pulses are half as wide in the time domain as the NRZ rectangular pulse, the RZ pulse will occupy twice the bandwidth in the frequency domain. The third filter we'll be using is the root raised cosine, or RRC, with a 30% roll-off factor. The root raised cosine is a very practical pulse that allows us to trade off bandwidth expansion against robustness to timing errors, for instance, robustness to jitter. We will include one fixed optical filter, and that is present mostly to filter the very wideband ASE noise. We will consider two types of electrical filter. The first, the match filter, and the second, a Bessel filter. The match filter will of course change as we change the pulse shapes. The match filter shape will also change. Let's return now to the block for the homework assignment. The first element is a laser source. We use an ideal laser source with no relative intensity noise and no phase noise. So it's a perfect monochromatic source. Next, we have an external modulator that accomplishes the electrical to optical conversion. We can use a finite extinction ratio for the external modulator, although I don't think it will be very important for the levels that we're considering in this homework assignment. Following the external modulator, we have a virtual combination of an ideal fiber and an ideal amplifier with gain G. These two elements taken together are essentially an all-pass filter. We assume that any losses in the fiber have been exactly compensated by the gain G. The noise properties of the amplifier are modeled by the spontaneous emission block. In this case, it's an additive white Gaussian noise. The optical filter that follows the ASC is used to limit the bandwidth of the ASC noise. Following the optical filter, we have the detection process where we accomplish the optical to electrical conversion. As we mentioned earlier, the photodetector introduces thermal and shot noise in the electrical domain. We include an electrical filter to limit the shot noise and thermal noise. Next, we sample our signal at the bit rate. Note that we'll be using 8 times oversampling in the simulation. Finally, we threshold the sample to decide whether a 0 or a 1 has been transmitted. When running simulations, one of the most useful tools you have for validating your results is to turn towards theoretical results. There will be certain regimes of operation where you expect your simulation to closely reflect theoretical results. So one of the first things we'll ask you to do is to plot the theoretical curves. Even the theoretical curves you could make mistakes on in your simulations if your normalizations of noise and other aspects of the simulation are not right. So what we're also going to do is validating the theoretical curves. So by doing that, we'll just pick a point and we'll calculate roughly what we think that point should be. When we plot our theoretical curve, we'll see if we do indeed fall to that point. So let's start with an exercise of validating the thermal noise. In this case, in the homework assignment, we're going to be looking at bit error rate at 10 to the minus 4. So I can start with the on-off keying. We know that the bit error rate is equal to 1/2 the error function complementary of the Q factor divided by the square root of 2. So if we want to achieve bit error rate equal 10 to the minus 4, that would mean that we would need a Q factor, which was equal to the error function complementary inverse of 2 times 10 to the minus 4 times the square root of 2, or 3.719. So now we can turn to an approximation for thermal noise limit from Agrawal. In the excerpts I provided you from his book on page 165, equation 4.618, I'll repeat for you here. It says that the received power is approximately equal to Q times the thermal noise variance divided by RD in the thermal noise limit. In our simulator, our homework assignment, we're given that RD is equal to 1.25, and at 10 gigabits per second, we can find that the thermal noise variance should be equal to about 1 microampere. So that would give us a way of calculating what we believe the received power should be. 3.719, 1 microampere divided by 1.25 amperes per watt gives us 0.003 milliwatts, or minus 25.3 dBm. So now I'll go and I'll plot in MATLAB my theoretical curve using the equations we learned in class, and I'll check at 10 to the minus 4. I have something like minus 25 dBm. And so this matches well, very well, good point at 10 to the minus 4. Implies that my theoretical curve is accurate. Once again, we're going to be validating some theoretical curves. In this case, we're going to be looking where we believe ASE noise is dominating, and again, to look at the 10 to the minus 4 bit error rate point. So we'll start with a few approximations from the ASE noise limit. We'll say that the variance for a 0 transmitted, which we'll call the spontaneous noise. There'll also be thermal noise and shot noise, but we'll assume that we're ASE noise limited. And the noise variance under the logical 1 would be the sum of the spontaneous variance and also the signal spontaneous variance. Now we're going to calculate our Q factor, and our Q factor by definition is I1 minus I0, sigma 0 plus sigma 1. And for high extinction ratio, we're going to neglect I0. I1 will be much greater than I0, so that's the first approximation for high extinction ratio. Next, I'm going to consider the relative values of sigma 0 and sigma 1. I'm going to assume that when we're working at 10 to the minus 4 that the transmit power will be higher than the ASE power, probably quite a bit, and I'm going to make the approximation that the spontaneous variance is much smaller than the signal spontaneous variance. And if this is the case, then I'm going to say that sigma 0 plus sigma 1 is approximately just sigma signal spontaneous. In other words, I'm neglecting the spontaneous noise. With these approximations, we get to the Q factor is approximately equal to I1 over sigma 1, or we'll call that our signal current, divided by the variance of the signal spontaneous contribution. Now we learned in class that this variance of the signal spontaneous contribution is given by 4 times the signal power, or current, excuse me, and the ASE current divided by the optical bandwidth multiplied by the electrical bandwidth. So we can simplify that a little bit. It's the signal current squared, optical bandwidth, 4 times the signal current, ASE current, electrical bandwidth, and of course that's just 1/2 square root of the signal current divided by the ASE current, and the square root of BO over BE. So what can we do now to try and find what our results will be? Well, we'll start out by saying that the signal current is the optical signal received power times the responsivity RD, the ASE current. Well, there's a couple ways we can look at this. We had an equation we saw in class that looked something like this, but another way of looking is saying it's simply the ASE power times RD, and a similar way for the signal. Same thing applies to ASE. And in this homework assignment, we're going to be given that the ASE power specified in terms of a power spectral density at a reference bandwidth. So we'll call it the PSD of the ASE at a reference bandwidth. And so of course we're going to have to multiply that by the optical bandwidth in order to get the PSD in the the ASE power within the optical bandwidth times RD. Fine. So next we can go back to our equation for Q, say it's about 1/2, and now what I have is the received power due to signal divided by the PSD of the ASE, and I'm going to get B bandwidth of the reference bandwidth divided by the electrical bandwidth. And in the homework, we're given that the PSD of the ASE is minus 35 dBm in a reference bandwidth of 0.1 nanometers, or the equivalent of 12.6 gigahertz. So now we can calculate what received power we think that we'll need due to the signal. So the received signal power should be 4Q squared, the electrical bandwidth, divided by the reference bandwidth equal to the signal received power spectral density of the ASE. And of course, in our case, it's 3.719 for the Q factor that we're looking for 10 to the minus 4. The electrical bandwidth of NRZ would be 10 gigahertz divided by 12.6 gigahertz. This leads to 16.6 dB, so that the power of the signal, received power of the signal in dBm should be equal to the power spectral density of the ASE, which is already in dBm, plus 16.6 dB, which gives us about minus 18.6 dBm. So now if I go into my generation of the theoretical curve for the ASE noise at 10 gigabits per second, I can see that at 10 to the minus 4, I have something just under minus 20 dBm, which corresponds pretty well to my calculated value of minus 18.6 dBm. So again, we have a good validation at 10 to the minus 4, which makes us believe that our plot of the theoretical curve is accurate.